Welcome back to our video module on mechanics of materials. I'd like to resume our conversation from our previous video on the coefficient of thermal expansion, or what happens when materials heat up. In our previous example, the sample went through some change in the temperature and as a result expanded. Then what I said is, let's pretend that we're going to constrict or confine the sample to some given length. Now we have to apply some sort of force to keep the sample from expanding. So I said that the strain due to the applied stress was equal to the strain due to the temperature. And if I wanted to be a little bit more accurate, I would have started off saying that the deformation due to the temperature equals the deformation due to some sort of applied stress. In this case, of course, the distinction really isn't substantive. These types of problems where there's an internal stress or an internal strain that happens because of the geometry or the temperature show up a fair bit. These are problems that can't be determined by use of simple statics. Hence, we call them indeterminate problems. And today, I'd like to think about how to approach these problems. For example, in our confined temperature model, we could think of it as some sort of bar that has an increased deflection plus a problem where you have this increased deflection that is experiencing some applied stress. This will cause the material to deform in this way, and we simply set the deformation of the thermal expansion equal to the deformation caused by the stress, and we have our solution. Another common problem that we might see is we'll take a cylinder and fill it with a rod, but the cylinder and the rod are different materials. So you can imagine they have a different Young's modulus. And we want to know, if we apply, some force, what is the deflection? Well, you know your equations that relate stress and strain, but we don't know how much of the force goes to the cylinder, right here, and how much of it goes to the rod, in here. What we do know is that the deflection of the cylinder equals the deflection of the rod. We also know that the reaction force on the cylinder plus the reaction force on the rod is going to equal the total applied force. So by looking at our problem setup, we can create additional equations that allow us to find the actual strain. Or we can imagine some sort of rigid rod sticking out from a wall, some applied force. But in addition, there are two ropes holding this rod up. The obvious question is, what is the deflection at A? We label our points B, C, and D, and once again, we use our problem setup to relate stresses and strains and the forces that each of the members is taking. In this case, using geometry, we could get a simple relationship between the deflection of C, the deflection of D, and the deflection at A. We also know that the sum of the forces in the vertical direction, that's going to be equal to 0. And the sum of the moments about point B is going to equal 0. Combining these equations, we can come up with relationships between applied force and the deflection that occurs, say, in rope C or in rope D. In summary, the setup is the hardest part of indeterminate problems. We can often use superposition to isolate two influences and identify an equation that relates them. We can often use the setup of the problem to come up with additional equations that allow us to solve for an unknown variable. I hope this gives you a better intuitive feel of how to attack these indeterminate problems. I encourage you to spend some time on your problem sets on these, because doing the problems is really the best way to feel your way towards analyzing constrained problems effectively.